So this is the last set of slides for Chapter 12 of Solutions. You should have already covered some of the other introductory concepts such as what is a solution, and the concentrations is how we express solutions. And this third part, we're going to look at colligative properties, Raoult's law, osmosis, and colloids. So the vapor pressure of a solution. The vapor pressure of a solvent above a solution is lower than the vapor pressure of the pure solvent. So if you have a mixture, it's going to lower the vapor pressure than if you had just the pure solvent. And this is because those solute particles are going to replace some of the solvent molecules at the surface. So here we have an example of a pure solvent, and it's going to establish an equilibrium. And notice that this is a closed system, so we've got a beaker and we've got a watch glass over the top, and we've got a solution. So we've got a solution here, we've got all the molecules in the liquid form, and above that liquid we have some molecules in the gas phase. So we have a volatile liquid. Now if we add a non-volatile solute, so something that does not evaporate, this is going to reduce the rate of vaporization. It's going to decrease the amount of vapor. So notice that we've added these little red particles. These are going to represent our non-volatile solute. So they're interfering with that process. And when they interfere with the process, you can't have as many of the solvent molecules going into the gas phase. So it's going to lower the vapor pressure above the solution. So if you have fewer molecules here, remember, the smaller the number of moles, the smaller the pressure. And we can remember that from our ideal gas law, PV equals nRT. So if we increase the number of moles, we're also going to increase the pressure. Or if we decrease the number of moles, we'll decrease the pressure. But this is just showing that even though once you add the non-volatile solute, that you'll again establish that equilibrium. So next I want to talk about thirsty solutions. So if we have a concentrated solution, it will draw solvent molecules toward it due to the natural drive for materials in nature to mix. So this is relating back to that concept of entropy. So rather than being concentrated, it's going to want to pick up more solvent molecules to dilute it so that it disperses it out and makes it more random, so you get a little more entropy. So similarly, if we have a concentrated solution, it will draw pure vapor into it, pure solvent vapor into it, due to this tendency of things to mix. And when this happens, the result is a reduction in the vapor pressure, like we saw on the previous slide. So we call this kind of like a thirsty solution. So an example of this, let's say we had two beakers. One contains a pure solvent, and then the other beaker contains a concentrated solution. So we have our same solvent in there, but we've got some other particles in there that's going to lower the vapor pressure. Now this system is a closed system, so we have this dome on the top that kind of keeps it closed. So initially we have pure solvent on the left and a concentrated solution on the right. Now as time passes, what will happen is that some of those molecules that are in the vapor phase can, they can escape above the solvent, right above the solvent, and they can pass through. We've got a closed system. So this entire jar area is going to fill up with the vapor from the solvent. Now as they fill up this area and it saturates the air here, these molecules can then go back into solution, go back in the liquid phase, or they can go in the gas phase, or they can go back and add to the other beaker where the same process is happening. But you'll notice here that the concentration on this side has gone down and the concentration on this side has gone up, or the amount of solvent molecules has increased. And what's happening is the solvent molecules are trying to dilute this concentrated area, and when it does, it has to take some from the other side. So eventually an equilibrium is established, and the liquid level on the left has gone down, and we have an increase on the right. In Raoult's law, basically it says that the vapor pressure of a volatile solvent above a solution is equal to its mole fraction of its normal vapor pressure. So if we were to express this mathematically, we have the pressure of the solvent in solution. So that's going to be proportional to the mole fraction of the solvent and the vapor pressure of just the pure solvent. So if you have a mixture, your mole fraction is never going to be 1. So you have a partial, you have a mixture, so it's going to be less than 1. So the pressure of the solvent of the solution is never going to be as much as the pressure of the pure solution. It's always going to be less than the pure solution. And it's going to be related by this mole fraction. Remember, the mole fraction is just the number of moles of the solvent over the total moles that you're looking at. So it'll be the moles. So the mole fraction. So the mole fraction of the solvent is the moles of the solvent over the moles of the solution. So that'll be the moles of the solvent and the solute. And because of the relationship between the ideal gas law, we can convert moles to pressure. So the pressure of the solvent to the pressure of the pure solvent. So that's how we can express this relationship. But since the mole fraction is always less than 1, the vapor pressure of the solvent in solution will always be less than the vapor pressure of the pure solvent. Now, according to Raoult's law, the effect of solute on the vapor pressure simply depends on the number of solute particles. Now, when you have an ionic compounds dissolve in water and they dissociate. So the number of solute particles is a multiple of the number of moles of formula units. So if we're looking at sodium chloride, since sodium chloride contains sodium and chloride ions, it'll break up into 2 pieces. So 1 mole of sodium chloride lowers the vapor pressure of water molecules twice as much as 1 mole of, say, sugar molecules would, just simply because the fact is when they dissociate, when they dissolve, they break into 2 things, whereas the sugar stays as one molecule. So the effect of ionic compounds on the vapor pressure of water is magnified by the dissociation. So let's look at Raoult's law for a volatile solute. So when both the solvent and the solute can evaporate, both molecules will be found in the vapor phase. And the total vapor pressure above the solution will be the sum of the vapor pressures of the solute and solvent. Remember, this is kind of like Dalton's law of partial pressure. We can add those together to get the sum vapor pressure. So for an ideal solution, the total pressure is equal to the pressure of the solute plus the pressure of the solvent. Now the solvent decreases the solute vapor pressure in the same way that the solute decreases the solvent. So just how we can say the pressure of the solute is equal to the mole fraction, the solute times the pressure of the solute, you can also say the pressure of the solvent is equal to the mole fraction of the solvent times the pressure of the pure solvent. Now there are ideal and non-ideal solutions, just like when we talked about gases, there are ideal gases and non-ideal gases. We have the same kind of thing where it doesn't quite work out as easily as we sometimes first describe it. In ideal solutions, the solute-solvent interactions that are made equal the sum of the broken solute-solute and solvent-solvent interactions. Solute-solvent interactions equal the solute contributions plus the solvent and solvent contributions. So if this were true, this would be an ideal situation, and it would follow Raoult's law. And if we looked at this graph, so here we have the expression of the mole fraction and the vapor pressure. So as the mole fraction of component A increases, we have an increase in the vapor pressure here, and we have the decrease in the vapor pressure of the solution. But not everything's ideal. If the solute-solvent interactions are stronger or weaker than the broken interactions in the solution, we say is non-ideal, and we get this deviation from what we'd expect in the graph. So it's when some of those interactions don't equal out to each other. So we're going to just talk about this in more detail in the next slide. So when the solute-solvent interactions are stronger than the solute-solute plus the solvent-solvent interactions, the total vapor pressure of the solution will be less than what's predicted by Raoult's law. So this dotted line here, this is what we'd expect for an ideal solution. But in reality, because some of those are stronger than, so stronger, if they're holding on more tightly, it can't vaporize as much, so it's going to be less than what we would expect for Raoult's law. And this is because the vapor pressure of the solute and solvent are lower than the ideal. Now when the solute-solvent interactions are weaker than the solute and the solvent-solvent interactions, the total vapor pressure of the solution will be larger than predicted by Raoult's law, because now you've got less energy holding things together than what was beforehand. So if you've got less forces holding things together, more can evaporate. So you got a slightly higher vapor pressure than what you would expect from the ideal line. So that dotted line again right here is the ideal, and it's higher than because those forces are weaker, so that more can escape. Whereas in the above situation we're talking about, they were stronger, so they can't break away, so you don't have as many going into the gas phase that we would expect, so it's less than ideal. So now let's take this information and let's look at a phase diagram. And phase diagrams were covered at the end of your Chem 1A, so this would be a little bit of a review for a phase diagram. So remember, in the phase diagram, you've got the different phases. So here we've got the solid phase, we've got the liquid phase, we've got the gas phase. And here where these three come together, that's a triple point. And going from this line to this line, we're going from solid to liquid, so this would be melting. Going from the liquid to gas, we do have vaporization. So this blue line represents the pure solvent. But notice what happens when we put in some solute into our solvent and we make a solution. Now we have the line right here, so that's what this red line represents. So here's we have the solution, and we have the solution here. So notice that going from the liquid to the solid phase, so melting, notice that it's melting sooner. So this is increase in temperature. If we have a solution, that's going to melt sooner, so it's going to lower the freezing point. And if we go from the liquid phase to gas phase, we're basically evaporating something. And when you're evaporating, you're boiling something, so it raises the boiling point. So the boiling point is when the pressure of the solvent reaches the atmospheric pressure. So here we've got the increase of the boiling point. So when you have a mixture, it's going to lower the freezing point and it's going to raise the boiling point. So you have boiling point elevation. So let's talk about the freezing point depression first. So the freezing point of a solution is lower than the freezing point of a pure solvent, and this will always be the case. And the freezing point we're talking about for a non-volatile solute, therefore the melting point of the solid solution is lower. Now the difference between the freezing point of the solution and the freezing point of the pure solvent is directly proportional to the molal concentration of solute particles. So molal is a way to express the concentration, so it's the molality, and remember this is lowercase m. Big M is molarity, little m is molality, and that's, remember, moles per kilogram of solvent. Now the freezing point depression is equal to the negative change in temperature. And so the change in temperature, that's at delta TF. So that's a change in the freezing point. Freezing point depression. Depression implies a negative sign. So that's why we have the negative change in temperature. And change in temperature is always final minus initial. So change is always final minus initial. So the change in temperature is the freezing point of the solution minus the freezing point of the solvent. So that we can get the freezing point expression, freezing point depression expression as the negative change in temperature times the molality times the Kf, and that's a constant associated with the solvent. Now I just want to make a little clarification here. If you see something that's slightly different in your book than the way I'm presenting it, delta is always final minus initial, so I disagree with how your book defines the change in the freezing point. They basically do this to get rid of the negative sign because of the implied freezing point depression, because it implies a negative sign. So the reason there is a negative in front is because of the implied negative sign in the name, freezing point depression. So if you ask what the freezing point depression is, and somebody tells you 3, that's well telling you that the freezing point is depressed by 3 degrees. So the change is a -3. Now the proportionate constant, that Kf, is called the freezing point depression constant. And that value of Kf depends on the solvent. And the units of Kf are degrees C per molality. And one of the things that you have to be careful of is always choose the Kf of the solvent, never of the solute. It's always for the pure solvent. So in this table, they're just listing some of the KF values. So for benzene, that's a solvent that you'll use in organic, carbon tet, chloroform, ethanol. So here they list the normal freezing points and they list the KF values for them. So remember, always the KF is associated with the solvent and not the solute. That's a common mistake people make on one of the lab experiments. So one of the things that you add to your car in the radiator, you actually add antifreeze. So that way, in case you go into a colder climate, the water doesn't freeze at 0 degrees C. It actually lowers the freezing point so that the water doesn't freeze and expand and explode your radiator. But when you add the antifreeze, you're also adding coolant, so that also raises the boiling point of the cooling water in your radiator. So you can't buy antifreeze without buying coolant. Sometimes it's a little bit of a marketing trick when they say, ooh, you get antifreeze and coolant. Well, you can't buy one without the other. That gives us the opportunity to talk about boiling point elevation. So boiling point elevation, the boiling point of a solution is higher than the boiling point of the pure solvent. And we saw this in the phase diagram. And here we're talking about a non-volatile solute. And the difference between the boiling point of the solution and the boiling point of the pure solvent is directly proportional to the mole concentration of solute particles. So again, the change in temperature is going to be proportional to the mole. So it looks very similar to the equation that we saw for the freezing point depression. So the boiling point elevation is going to be equal to the molality times the boiling point elevation constant. So the change in temperature, that change, that delta, the boiling point is going to be equal to the molality times the Kb. And this is a type of colligative property. And colligative property means it doesn't matter, what kind of solute that you added to it. It just matters how much that you added to it. So that's why we're using the molality. It doesn't care, what type of solute you add to it, as long as it's a non-volatile solute and you know the molality of it, so you know how much you added to it, you can figure out the change in the boiling point when you add that solute to the solvent. So online in Blackboard, you should be able to find this osmosis video, or we may be able to show it in class. But it describes what osmosis is. But what you'll see in the video is initially you've got water molecules on one side of this semipermeable membrane, and on the other side you have these solute particles and just a few water molecules. But what happens is, because of the tendency of things to mix, the water molecules will move through this osmotic membrane and pass through to dilute this concentration over here, because it wants these concentrations on both sides to be the same. But it won't ever be the same, but it's going to try to reduce the concentration, so the water is going to flow in here. Now the thing about this membrane here is that the pore size is so that water can flow through, and whatever these solute particles are, they can't pass through this membrane, so they're actually too large to pass through, so only the water can pass through. So to lower the concentration of this, the water is going to move over through the membrane, and it's going to dilute the concentration over here. So we have a net movement of water to the right side, and we have a flow of solvent through a semipermeable membrane from a solution of lower concentration to a solution of higher concentration, so it can dilute that higher concentration. So osmosis, if we define that, it's the flow of solvent through a semipermeable membrane from a solution of lower concentration to a solution of higher concentration. And the amount of pressure needed to keep osmotic flow from taking place, this is called the osmotic pressure. So here we have, this U-tube here. We've got a semipermeable membrane, and we have some solvent particles on this side and some water molecules. We have water molecules on the other side. And if we allow time to pass, eventually the water molecules can pass through, because only the water molecules can pass through, the solute particles can't. They're going to pass through the other side. It's going to raise the water level on this side. And it's going to increase until you get to the osmotic pressure. So the pressure of excess fluid is going to equal to the osmotic pressure of the solution. So the pressure that the water molecule is trying to get in here, but you got the force of the molecules over here, or sorry, the force of the atmosphere pushing down on the side, trying to push back. So it eventually bounces out to reach that osmotic pressure at equilibrium. So the pressure of excess fluid is equal to the osmotic pressure. Now the osmotic pressure, so we're going to relate this with this big pi, this capital pi here, is directly proportional to the molarity of the solute particles. So remember, big M is molarity, R is our gas constant, so we're using the one with units of liter atmospheres per mole K, and T is the temperature. So the osmotic pressure is going to be proportional to the molarity, the gas constant, and the temperature. So the osmotic pressure and the freezing point depression and the boiling point elevation, those are all examples of colligative properties. Colligative properties are those properties which values depend only on the number of solute particles, and they don't care what they are. So it's how many are there and not what they are that will determine the amount of the change in the colligative property. So examples include vapor point depression, freezing point depression, boiling point elevation, and osmotic pressure. Those are all colligative properties. Now, when we were talking about some of these colligative properties, we were talking especially with the boiling point elevation and freezing point depression, we said we're only talking about non-volatile solutes. This is because when you're talking about colligative properties that depend on what's there, if you have something that ionizes, you have more things that go into solution. And not only that, if you have something that ionizes and you've got charged particles, you still got some interactions between the cations and the anions. And we take this into account when we use the Van Hoff factor. So the Van Hoff factor, we're going to abbreviate with the lowercase I, is the ratio of moles of solute particles to the moles of formula units dissolved. So if we're talking about sodium chloride, remember sodium chloride breaks up into two things. We've got a sodium and a chloride. So we would have a Van Hoff factor of 2. So we see this in this table here where we have the expected in this table here we have the expected Van Hoff factors. So if you have a non-electrolyte, so something that's non-ionizing, it's going to stay whole like the sugar molecule like sucrose. So we'd only have a value of 1. If it breaks up into 2, like sodium chloride, we expect 2, or magnesium sulfate breaks up into 2 things, we have a Van Hoff factor of 2. Magnesium chloride breaks up into 3 things. Potassium sulfate breaks up into 3. Iron trichloride breaks up into 4. So these are the Van Hoff factors that we would expect. But in reality, these are a little bit different when you actually measure them. Because what happens, let's look at the case of sodium chloride. We'd expect 2 because we produce 2 particles when they dissolve. But the measured one is slightly less than 2, so it's 1.9. And the reason why it's less than the 2 that we'd expect is that sometimes you get some ion pairing in solution. And what does this mean? Well, you got some of these that, yeah, even though the sodium's solvated by the water molecules here, and this chloride's solvated by the positive ends of the water molecules here, they still can kind of detect each other, and they kind of get close enough, and they kind of cancel each other out and kind of act as one. But the majority of these are all acting as individual units. So this is why you sometimes get something that's a little less than the 2 that we expect, because we have this ion pairing that can occur. And notice for like iron trichloride, we have a much bigger deviation from the iron chloride. So imagine an iron 3+, and you've got 3 chlorides. And because this has a higher charge, that iron 3+, it's much more likely to ion pair with one of these other chlorides. So that's why you have a larger deviation from 4 for the iron chlorides. So it's 3.4 versus the expected 4. So you're much more likely to have an ion pairing due to the higher charge. So here I just want to go back and talk about some of the osmotic systems. So here we have 3 red blood cells. One, we have an isoosmotic solution. So this is a normal red blood cell and how it looks. So it's kind of discus shaped. We've got the little indentation in the center here. But if we were to put that into a hyperosmotic solution, notice how the red blood cells all shriveled up. If we have it in a hypoosmotic solution, the red blood cell gets very swollen. Isoosmotic solution has the same osmotic pressure as the solution inside the cell as on the outside. So if you got the same osmotic pressure inside and outside, you're not going to have any net movement of fluid in and out. So you're going to have that nice maintained shape. So in this case, the osmotic pressure in going to be the same as the osmotic pressure on the outside of it. Now, a hyperosmotic solution, hyper meaning more, so think of somebody that's hyperactive, they got more energy. That hyperosmotic solution has a higher osmotic pressure than the solution inside the cell. So as a result, there's going to be a net flow of water out of the cell, causing it to shrivel. So in this case, the osmotic pressure inside is less than that of it outside. So it's greater outside, so what's going to happen is the water is going to flow out of the cell to the outside, and it's going to cause it to shrivel up because it doesn't have as much fluid on the inside. So this is what happens when you have a hyperosmotic cell. If you have a hypoosmotic solution, you have a lower osmotic pressure than the solution inside the cell. So the osmotic pressure inside is greater than the osmotic pressure outside the cell. And if it absorbs too much solution and too much water passes through it, the cell can actually burst. So this is why it's important to maintain a good osmotic pressure and maintain the electrolyte concentrations inside and outside your cells. Okay, so one of the last things that we'll talk about in this section are colloids. These are other types of mixtures, and they're kind of in this kind of gray area when we talk about homogeneous and heterogeneous mixtures. Because the particles are so small and tiny and suspended, you can't really think about it as a heterogeneous solution, but yet it's not truly a homogeneous solution. So it's kind of this gray area when we're talking about colloids. And a colloidal suspension is a heterogeneous mixture in which one substance is dispersed through another. And it almost looks like a homogeneous solution, but technically we'll classify as a heterogeneous mixture. It's just that what's in there are so small it kind of looks homogeneous. But we'll see ways that we can prove that it's really heterogeneous in nature. Most colloids are made of finely divided particles and they're suspended in a medium. And the difference between colloids and a regular suspension is just generally particle size. So colloidal particles are from 1 to 100 nanometers in size. So they're very small. And notice that here we have a colloidal suspension, and on the other side of the glass we have pure water. If we would shine light into it, the little bitty particles that are in there, even though you can't really see them on the slide, the light is actually being diffracted by them. So it scatters the light, and you kind of see the light passing through due to the scattering of the suspended particles. Whereas in the pure water, you don't see that effect. So this is actually an example of the Tyndall effect. So we're going to look at some properties of colloids. Now, some of those properties of colloids, first of all, they experience Brownian motion. So this is very random motion, so they'll move around in every which way and very random like patterns. So we call this Brownian motion. And the colloids also exhibit the Tyndall effect, so it scatters light as it passes through this suspension. And colloids scatter short wavelengths, so blue light, more effectively than longer wavelengths of light, so the red light. So that's why you kind of see this haziness here, so either due to some smoke or suspended vapors in the air, like fog or something like that. So we also want to take this time to discuss soap and Micelles. So here we have a bar of OLAY soap, and it lists some of the active ingredients. We have sodium coil, isethionate, paraffin, sodium, lots of long words, glycerin, water, talc, magnesium stearate, stearic acid, sodium, isethionate, magnesium. So it's got a big long list of all these chemicals that are in there. And one of those things I want to show you, I've highlighted the magnesium stearate. This is actually a picture of sodium stearate, so you've just got a different counter ion. So rather than the magnesium to balance the charge, we've got a sodium here. The sodium stearate, you've got this long end of the soap molecule. So you've got this long chain hydrocarbon, lots of carbon, lots of hydrogen, carbon bonds, lots of carbon hydrogen bonds. So we expect this end of the molecule to be nonpolar. So you have lots of dispersion type forces with this end of the molecule. But at this end of the molecule, you've got a carbon-oxygen double bond, and you've got a carbon-oxygen bond here with a negative charge. So this end, you've got this ionic head. So you've got these two parts of the soap molecule that have very different components. You have the nonpolar end and the ionic end. So you expect the ionic end to interact really well with water and things, but this end you would expect to interact really well with nonpolar things like fats and things. So this is how soap actually works. This end of the soap molecule interacts with the fats and the oils and the greases, and it traps them and it attaches on. But the polar end of the molecule, this ionic head, makes it water soluble, so you can actually kind of dissolve and pick up and carry the soap and the fats and the oils away. So this is what you're doing when you're using the soap. You've got this one end, so it makes it more water soluble. Now, one of the things that this does is it wraps around, it creates what we call a micelle. So you have all these nonpolar tails interacting with the fatty, the oily, and the greasy stuff. So they're interacting with that and they wrap around it. And then the heads of it all wrap around the outside, and so it creates this micelle structure. And so it's able to dissolve in the water. So this is how soap works. So it's actually really kind of cool. So most dirt and grease is made up of nonpolar molecules, making it hard for water to remove it from the surface. So remember, oil and water don't mix. So just trying to wash your clothes that are oily and greasy in water doesn't really get them clean. You have to add soap to it. So the soap molecules form micelles around the small oil particles, and it causes the polar and ionic heads to point out. And this allows the micelle to be attracted to the water and it stays suspended. So when you rinse your clothes, you rinse off the soap and the micelles, and it takes the dirt away, and you actually clean your clothes that way. So other than just cleaning yourself and cleaning your clothes, how can we apply some of this information? We can also apply this in the kitchen. So other than just the lab, we can apply it in the kitchen and making salad dressings. A lot of salad dressings are vinaigrettes, so you've got a mixture of vinegars to flavor things, and you've got oils. We also said, remember, that some of the vitamins are fat soluble, so having some oil in your salad dressing is actually a good thing. But if they don't mix very well, it's kind of hard to get it on your salad. So one of the things that chefs do to kind of get these two to mix, they create an emulsion. And the way that they do it, so here we have a picture of an emulsion on the right hand side. They add things to the oil and vinegar mixture, such as mustard powder or finely chopped herbs or egg yolks, and this creates an emulsion that helps bring the two together, kind of like what we saw with the soap particles. And then the last slide is just kind of going through other types of colloidal dispersions, not just liquids. You can have aerosols where you have a liquid and a gas, or solid aerosols where like smoke in the air. We get some solid particles in the air, so you got a solid and a gas. You can also have foam. So an example would be whipped cream. So you have air bubbles trapped inside the liquid. So you can also have emulsions. So milk is an example of emulsion. You have a liquid in a liquid. You have those fat globules suspended in the milk. So we have homogenized milk to make it nice and uniform. You can also have solid emulsions. I think this is kind of cool because opals are a really good example. You actually have water trapped in silica glass. So you have a liquid trapped in the solid. So this is actually an example of a solid emulsion. You get these really pretty effects from the opals. That ends our Chapter 12 discussion and introductory material.